Welcome to this latest video. In this video, we'll be referring to the OCR exam topics of 2.3, producing robust programs, 2.4, Boolean logic, 2.5, programming languages and integrated development environments. All the subtopics you can see on the slide are the ones we'll be doing, and we're going to do all this under this rigmarole of logic and languages while we're looking at a bunch of exam questions. Okay, let's get to it. Okay, let's look at this question. The question is asking us about the concept of defensive design. So this is when you're thinking about when you're developing code, how are you going to make it so that when users enter values, it doesn't break it, or will you anticipate what people might enter in terms of data so that you can actually catch those mistakes and stop them becoming a problem. And we're including things like testing, and how we can actually think about problems and use things like validation to eliminate those problems. In this scenario, a car dealership uses a computer system to record details of the cars that it has for sale. Each car has a make, model, age, and number of miles driven. Each car is given a star rating of 1 to 5. Okay. Based on the age of the car and the number of miles it has been driven, the rating is recorded in the computer system. Define the term abstraction. So along with decomposition, algorithmic thinking, these are one of the key computational thinking terms we have to understand. So I may define abstraction as removing unnecessary detail. And we do this because we want to be able to focus on the essential components. We want to focus on the essential components of the system. Now it's asking us to give one example of how abstraction has been used in the design of the star rating system. So remember, we're about removing unnecessary detail from the problem to allow us to focus on the essential parts. So it's asking us really, what kind of details were not needed? Well, let's have a quick look about what was used. They used a computer system to record the cars that's for sale, fine. And what did they use to establish how good a car was? They said the car has a make, model, age, and number of miles driven, and each car has a star rating of 1 to 5 based on the age of the car and the number of miles it has been driven. So age and the number of miles, that was what we focused on to allow it to be used. So now we can talk about, okay, well, what sort of thing were we not used? Well, we focused on the age of the car and the number of miles. So what did we not focus on? Well, we're holding information like their make, model, age, and number of miles. Age and number of miles we focused on, so it must mean that we didn't consider the make and model. So we ignored other factors such as make and model. Great. Okay, let's move on now. Explain how authentication could be used as part of the defensive design considerations for this computer system. Now, if you remember, authentication, one of the areas of operating systems, but essentially we're talking about where you're proving you are who you say you are. So that could be via username and passwords, could be via biometrics, could be a bunch of different systems. We want to authenticate that the user is who they say they are. But how do these users prove that they are their own identity? And we now need to give an example. So for instance, that could be by using username and passwords, could be using biometrics. If you remember, biometrics is when you use something about yourself, such as your fingerprint, to identify yourself. Another question on defensive design and some of the things we need to consider, some of the factors. Elliot plays football for OCR Football Club. He wants to create a program to store the results of each football match they play and the names of the goal scorers. Okay. Elliot wants individual players from the team to be able to submit this information. Describe 2 examples of defensive design that should be considered when developing this program. Okay. First thing we need to think about are what are the defensive design considerations that we'll need to think about when writing code. Now, they've given you some ideas here because they're saying Elliot wants individual players from the team to submit the information, such as the number of scores. Well, what happens if they make a mistake. They maybe they want to put in 2 goals, they hit the 2 twice, and they put in 22 goals. So we need some way of actually restricting the kind of data that somebody can put in, and to achieve use of something called validation. There are lots of different types of validation we could use. There's something called range check. This could be, for instance, limiting the minimum number of goals you can input to 0 and the maximum to be maybe being, I don't know, less than 20 or something. And that by helping restrict the amount of answers, making it a bit more sensible. There are other examples such as type check, where saying you want the data inputted as an int, because otherwise they could perhaps input it as a string, typing TWO. Format check, so maybe there's a format for how you want the data to be entered. This is often used for things like postcodes, because there's a particular format. And presence check, that would be that it can't be empty, that you're requiring that the person actually enters some score there. However, you could still put in totally the wrong score. Even though you're saying you're using a range check to make it between, say, 0 and 20, you could easily enter, say, 15 goals when it should have been 1 goal. So you can also add another thing to the pile, not validation, but verification. Verification is checking that you've actually done it correctly. A classic place where you may have seen this is in what's called double entry verification. When you enter your password onto a new website, typically you're asked to enter it twice. It compares them, and if they've been entered correctly or they match, then it's allowed to pass. Okay, well, let's say we've now, it's validated and it's verified, and I know you've only been asked to identify 2, but it's worth exploring some of the others. Well, based on our last question, do we need to have it so that even though additional teammates can add it, they still need to prove who they are, right? Because otherwise you could have people who don't have access entering it. So we call that proving that people are who they say they are, authentication. And as you remember from last time, the way that you prove who you are, you could be doing by username or passwords or biometrics, for instance. Great. Well, this identifies a lot of the defensive design considerations we want to make. But it could also be that you're thinking about in the future about making your code robust, i.e., let's say you've made not a syntax error, but a logic error that you haven't spotted. You come back to your code at a later point, you might not be able to find out where that issue is because it's actually not laid out nicely, or it's not commented, or you're working in a team of programmers and somebody else is looking at it. You want to allow other programmers to understand how your code works. And we call that maintainable code. How do we do this? How do we make our code more maintainable? Well, some of the key ones will be to indent, make use of meaningful variable names. In your code, of course, you should be commenting what your code does. And also potentially, and I've run out of space here, use things like subprograms to allow it to be more modular. Now, we've got 4 different considerations then: validation, verification, authentication, and maintainable code. To answer this question, we basically need to pick 2 out of these, and I think I'll go for validation to get started. What do we mean to validate? Does that mean to make it so that the user has to enter the right information? No. We should say that it's allowing the inputted data to be more sensible or to follow the criteria depending on the check. So I'm saying whether it's sensible. What else do I need to add in here? I should add an example. So how about a range check so that goals should perhaps always be above 0? Great. Well, what do I do for the next one? Well, I've got verification. I think that's a pretty strong one to go for. If you remember, this is when you're checking that the information has been entered correctly. What's an example of this? Well, for instance, it could be entering the name of the scorer twice and comparing. Great. On to the next one. So as discussed before, part of defensive design is making sure that people in the future, maybe yourself or another programmer, can work on your code. Maybe there's an error, maybe they need to tweak something about it to improve it. And we call that maintainability. And there's certain things you can do to help maintain code. In this question, the area of a circle is calculated using the formula pi times r squared. Finn has written a program to allow a user to enter the radius of a circle as a whole number. here in the radius. It's an integer, a whole number, between 1 and 30. And output the area of the circle. Here is our code. Explain using examples from the program 2 ways Fin can improve the maintainability of our code. So we'd have to have a look through here and think about some of the things they may be making use of. So remember, when we're thinking maintainability, we need to be thinking about the following things. We need to be thinking about indentation. We need to be thinking about meaningful variable names. We need to be thinking about things such as making use of comments. And actually it occurs this time because we're using variables, but sometimes we have a value that is not going to change. In this case, we've got pi, and pi immediately makes me think, maybe we could hold that as a constant. Why is it sensible to make use of constants for things that aren't going to use? Well, it stops people accidentally changing the value of something such as pi, and it sort of eliminates those further risks of that changing and then making it come up with the wrong calculation. All part of defensive design and maintainability. So I need to pick 2 of these examples, and since it's 4 marks, I also would have to explain how it works and link it to this bit of code, of course. So looking through this bit of code, I see straight away something they've got missing is indentation. So here, for instance, in the if statement, that value here, the print, that should be indented, shouldn't it? So I'm going to pick that as my first, and I'll say it's to show the scope of code where constructors begin and end. What example can I see here? Well, my example will be the if statement. So I'll say on line 5, print should be indented. What else can I make use of here? Well, constants could be one, because I could set the pi as a constant. But I think a really good go-to one here, because I can't see any of it, is that I can't see the use of comments. Truthfully, the variables have relatively meaningful names, but I think the big one here was the use of comments. And remember, you use comments either to yourself in the future, but more typically to other programmers to explain how the key functions work. Maybe a good comment here would be for this if statement to explain that the way the if statement is going to work, it's a range check validation. Of course, you could have picked some other ones, and I believe at the beginning I said it was a 4 marker. Actually, it's a 6 marker. Where are you going to get the marks? Mark for identifying indentation, mark for identifying comments, mark for explaining what it does, and a mark for then applying it to the context here. So that would be 6 marks for this one. So now we're continuing with the idea of how do we produce robust programs. And again, by robust, we mean programs that don't break easily on certain kind of inputs, that don't have errors which give the wrong kind of results. And the way we establish whether your program is robust or not is by making use of testing. So we're going to have a look at that topic now. Louise writes a program to work out if a number entered by the user is odd or even. Her first attempt at this is the program shown below. We have 6 lines of code here. The input of the asked to request an input stored as a num. This is pseudocode, so it's not following the convention of something like Python, where you'd have to then cast that as an integer. If num mod 2, so remember mod is modulus for the division, I'm sure we'll come to this. If it is greater than or equal to 0, then print even. I might have seen an error here. Else print odd, and if. The program contains a logic error on line 2. Yes, I think we spot it. What is meant by a logic error? So remember, syntax errors are where the program won't run because you can't translate it, can't compile it, because you are not following the rules of the language. Syntax errors you will come into probably very frequently when you come up with like red squiggly lines. The IDE might be trying to tell you it doesn't work, and if you try and run it, it just says that there's an error and you get a bunch of red text complaining about it. But logic errors are different. What is the main difference? Well, the main difference you have with a logic error is that the program will run. So the program will run, i.e. it will be translated to machine code and then run. So what's the problem? Here's the problem. It doesn't do what the programmer intended. Whereas if it was a syntax error, the program would not run. Give a corrected version of line 2 that fixes the logic error. So it's in here. I wonder if you can spot it. Remember, the way that mod works, it's the remainder. So let's say we had 1 mod 2. The way it would work is it would say, how many 2's can you put in 1? And the answer would be, you can't put any in. And then what's left over? Well, the leftover would be 1. And then we can try it with 2 mod 2. How many 2's can you put into 2? Well, the answer is 1. But what's left over? Nothing's left over. So it would be 0. So if we follow it here, 2 is at 2. If you mod 2, is it greater than or equal to 0? Well, if it was 1 mod 2 is equal to 1. 1 is greater than or equal to 0, so it'll print even. If it's 2, would that be greater than or equal to 0? Yes. So whatever you put in here, it will always return even. What's the solution? Well, the solution is to change this bit here. I'll give you a moment to think. Pause if you need to figure out how you might fix it. Right. So what we'll need to change is this bit here, is the comparison. Not greater than or equal to. We want to make it equal to. You might be thrown for a second, why have I used double equals? Well, remember, a single equals is for assignment. So here, single equals is assigning a value to a variable. Double equals is for comparison, which is what we want to do here. It's also worth pointing out that you might have forgotten the phrase mod, but in Python that would be the percentage sign. Now we've been asked, we've been informed that on line 5, so here there is an error, a syntax error. And we have to state what is meant by a syntax error, so we have to give a clear definition. So my definition would be, lead with the program will not run to distinguish it from a logic error where the program will run. But why won't it run? As the code breaks the rules of the language. It breaks the rules of the language. And can we see where the error actually is? Well, if you look, it's printin', i.e. it's a new, this is a command word that we identified, print, to output. But printin' isn't anything. It might think it's a variable, but then it would expect an equal sign at the end of it. So we need to go fix that now. So what we'd have to do is then write out how it should actually look. I wouldn't get lazy. I wouldn't just write print. I would write the whole line out. Now we're going to make use of the learning we've just done to rewrite some code. So this is a very kind of classic question you might be given, where you're given some original code and then asked to fix any syntax and or logic errors you may see. Let's have a read of the question. An item is classified as in demand if OCR tech has between 5 and 25 inclusive. And inclusive is doing a lot of work for us right there. It's saying when we get to 25, that should be okay. When it's 26, then it's gone too far. So it includes 5 and 25. A program is written that allows the user to input the current stock level and output whether the item is in demand or not. So depending on whether it's between 5 and 25. Stock level equals input enter stock level. So you can see in here, that wouldn't work for us for Python again, because we want that to be an integer. So we'd want to cast it. If the stock level is greater than or equal to 5 or less than or equal to 25, then print not in demand. And we'd want to put speech marks around there. Now that's where we might have an error. And print in demand is the issue. Okay, so one of the things I always do in these scenarios is I try and feed in some concrete data. So why don't we think, we're saying that 5 should be acceptable, so that would be a borderline case. So let me just do that a sec. I'm going to feed in 5, but I should also feed in maybe 25. And then let's go on the other side where it's invalid. So that would be 4. And then maybe 30 and see what happens. So I'm anticipating that 5 and 25 are my borderline values that are still valid. So it should say, if we look, if the stock level is between 5 and 25 should say in demand. So 5 and 25 should say in demand. 4, because it's outside that, should say not in demand. Okay. 5. Is 5 greater than or equal to 5? It is true. And remember, with an OR statement, if just one side is true, then it will be true. If both sides are true, it will be true. For only way it can be false if both of them are false. So 5 is greater than or equal to 5, so it will say not in demand. Oh, immediately we have an issue here. 25. Is 25 greater than or equal to 5? Yes. So it will work, and it will say not in demand, so it's giving us the wrong value again. 4. Is 4 greater than or equal to 5? No. Is it less than 25? Yes. So it's still not in demand. In fact, there is no number that's either greater than or equal to 5 or less than 25, because every number is either greater than or equal to 5 or less than or equal to 25. So right here, the program will run, but it won't do as we intended, i.e. in here we have our logic error. Why don't I just start writing out the code here? I'll make the change, which is to put an int, to cast that as an integer for our Python programming language. And then we'll have a think about how we're going to solve this problem. Also remember, we're either doing OCR exam reference language or we're doing a high-level programming language, for us Python, so we have to be correct with the syntax. First, I'll define the variable, and then I'm going to do my input. Now remember, in Python, if you do it like input like this, the data will be taken in as a string. And because I want to do a numerical logical comparison, I need to change that. I need to cast it as an int. And I do that by writing int here and putting all of input inside that bracket, i.e. that will come out as a string, and then that will be an int. We'll convert it to an int. I'll then write an if, like it's done in the problem. Now, this is the problem here that we'll need to fix. So we're saying actually that it's greater than or equal to 5 or less than or equal to 25 is not in demand. Well, truthfully, that's never going to work. There's two ways of doing this. You either can describe what you don't want. So I could say if stock level is less than 5 or greater than 25, not in demand, so that would work. Or you can define what you do want, in which case stock level greater than or equal to 5 and less than or equal to 25 is in demand. I'm going to describe what I am looking for. The first comparison is stock level greater than or equal to 5, and then I'm going to link it with a and instead of an or, and on the other side I'll do stock level is less than or equal to 25. Remember, I now need to continue to follow the rules of the Python syntax, and that would mean I'd have a colon at the end. The next statement I need to do, if you do it directly underneath, that's a big problem, because in programming languages you should indent for readability and to help maintainability, but in Python you need to indent in addition to describe the scope. So I need to say, if I put it here, it means it's happening inside the if statement. If I put it over here, it's happening outside. So I need to start here. And what do I need to say? Well, I'm describing that's what I am looking for. So this time I'll print in demand. I'll have to do the other side, so I'll do the else. What is it I have to put at the end of the else if I'm following the rules of Python? That's right, I'll do a colon, and notice how the else is in line with the if. The print command I need to do needs to be inside the else statement. There we go. And as I say, you could also do this by saying if stock level is less than 5 or stock level greater than 25, print not in demand, else print in demand. So that's your different options. What we got here is a repeat of one of the previous questions in the sense that Charlie is writing a program for music students. To make sure there are no logic errors in the program, Charlie uses a test plan. So that's the new bit of learning we're going to do. Describe what's meant by a logic error. So why don't you have a go at trying to do that? If you're not too sure of the definition, you can go to the previous question and I covered it there. Big picture is the program runs but doesn't do what the programmer intended, as opposed to a syntax error where the program will not run and will, because it's not following the rules of the programming language. On the other side, we say the program uses letters in the following list to represent musical notes. These ones here, C, D, E, F, G, A, B. Okay. When the user inputs a letter from this list, the program outputs the next 3 notes in the list. If it gets to the end of the list, it starts again from the beginning, so the next note after B is C. Complete the test found below by stating for each input the exact outcome and a reason for the test. Let's think about the different reasons for a test. So we've got 4 main reasons, and these are testing for valid inputs and to see if it works. Testing for values that are invalid, so that's outside of the range that is normally expected. Testing to see for borderline or extreme, so right at the edge of what's still valid. And finally, erroneous, so this is sending in, for instance, if it's expecting it to be characters, you could send it Booleans or integers to see what happens under those ones. So those are our different categories. So we've got 3. The 3 you normally want to go for are valid, invalid, and borderline examples in the ones here. And we have to think about what it's going to be. So how about we start off with just sort of a valid one, just a normal test. So they've actually already given us the input data. So for C, we're expecting it to be C and then D, E, F, the next 3 letters. So that would be, the expected outcome would be D, E, F. This is our fairly standard test, and I guess ultimately it's checking that it will print out the next 3 values under standard conditions. Our next test is with A, and if we look at A, what should happen? It should go B, C, D. So this is more or less our kind of borderline test, really. We're checking to see whether it actually goes around and back to the beginning. So if we're inputting A, it should be B, C, D. And what we're trying to do, well, we're trying to check that the output, that we go back to the beginning of the list when we get to the end. We have a final test for H. Well, H, do you see, is not in our list. It is the right data type, so it's not erroneous, but it would be what you would consider a invalid input. Does it say what happens? When the user inputs a letter from the list, the program outputs the next 3 notes. If it gets to the end of the list, it starts again. It doesn't actually say what happens, but I guess what we'd hope to happen is that there's some kind of an error message. And why do we do this list? Well, we're testing it with invalid data. Great stuff. Okay, a bit of continuation with testing now. And you can see they're talking about normal, what I referred to as valid, and boundary data, which can also be thought of as extreme data. We've got missing invalid and we've got missing erroneous. So we've got these 2 that we can actually review. And what it's asking us to do is that it's drawn up a test plan for us to do. And we have to say, using this flowchart, what the expected price output is going to be. Okay, so we start at start. Remember, parallelograms like this, those are for inputs and outputs. The diamonds are for decisions, so for showing selection or loops. The rectangles like this is for a process, so it's going to do something. And then finally get to the end, and we obviously follow the arrows. So the first one is price is input 50. So that's input here. Is 50 greater than 200? No. Is it greater than 100? No. And we follow this down, output the price to the user. So expect the outcome, in this case, to be 50. Great, let's do the next one. 100. Input the price. Is 100 greater than 200? No. Is 100 greater than 100? No. Output price 100. And this is boundary because these would be one of these tests. Do we mean greater than, or did we mean greater than or equal to, right? Teasing out those logic errors that are at the boundary. Please feel free not to have to watch, pause, and have a go at doing it yourself right now. I'm going to continue to go through this. So 150, greater than 200? No. Greater than 100? Yes. Reduce the price by 20, so it's 150 minus 20, so 130, and output the price. We have another boundary question. Why is it boundary at 200? Because that's where the edge is. Is 200 greater than 200? No. Is it greater than 100? Yes. So take away 20, so giving us a result of 180. And finally, 250. Is 250 higher than 200? Yes. Take away 40, so giving us 210, and then outputting the result. Okay, and with this question, we're continuing to look at testing, But now we're looking at testing from the perspective of why do we test? What are we trying to achieve when we're testing? And also, what is the difference between iterative testing and final testing? The scenario we're given is a vending machine that has the following options available. So we've got these options about things that you can buy in this vending machine, the item and the price. The user insert coins into the vending machine and then enter the 2-character item code of the selection. So they say if you put in 30p and you put in C1, you don't actually have enough money in this case. So if the user has inserted enough money, the vending machine will release the chosen item and output any change. If the user enters an invalid code, i.e. a code that doesn't exist here, then a suitable error message is displayed. Okay, so that's how this little system works. The vending machine is tested before it's released. Explain the purpose of testing the vending machine. In this context, we can give reasons as for what testing is, why do we give testing, but we also should try to link it in some way to the vending machine. So let's have a think about some of the things we might want to say. What is it we're trying to achieve when we're testing? If you recall, there are two different types of errors. There are syntax errors, and then there are logic errors. With syntax errors, the program won't run. So we're really looking at logic errors here. And what was the definition of a logic error? A logic error is when the program runs, but doesn't do what the programmer intended. So we need to be looking for that. So what we might say is something like that the program meets the user requirements. Because bear in mind, you don't know whether it's a logic error or not. It becomes a logic error if it fails to meet the requirements of the user, hence doesn't do what the programmer intended. Indeed, we can say we need to check the program works as intended. That's why we can see if there's a logic error or not. Why do we test? Well, we test because we can identify those errors which can then be fixed. What we haven't done so far is actually link this back to the vending machine. So let's give an example of what that could be. I could say something like, meaning the vending machine only gives the item when the user has entered sufficient credit, i.e. sufficient amount of coins. We now need to consider the difference between iterative testing and final testing. Now, iterative does not sound a little bit similar to iteration. This is when it's repeatedly tested whilst making changes. So this is during development. Iterative testing is happening during development where you're testing repeatedly while you're making the changes. Final testing, so this iterative testing is almost certainly what you have been doing as a software developer so far. But final testing is once you've actually made it, when it's complete or almost complete and is done after iterative testing. So final testing is when the development has been completed. So you finish your code base and then after iterative testing, and you're kind of looking for final bugs or logical errors that you've missed whilst your development. Final question on testing, on producing robust programs. In this case, we've been given a scenario. The program should only allow values from 0 to 300 inclusive. Remember, inclusive means that we need to include 0 and 300 as valid. If the data entered breaks this validation rule, an error message is displayed. Do you remember what kind of a validation rule this is? When you're saying it's got to be between 0 to 300, between a range of values? That's right, it's a range check. Complete the following program to output invalid input if the data does not meet the validation rule. You must use either OCR exam reference language or a high-level programming language. And in this case, as before, we'll be using Python. In here, technically we've broken it straight away because it should say mins equals int input to cast it as an int. So we'll ignore that, I guess. If mins is less than 0, something, then something down here. So if you remember, we did this previously, and we said we can either describe what we're looking for, or we can describe what we are, or what we're looking to include. So in this case, if it's less than 0, then we're looking at what we maybe are invalid. So if it's less than 0, or so if the mins is less than 0, or if mins is greater than 300, so this is outside the range, then what? Then print invalid. Fantastic. And then we have a test plan here we need to have a look at. Remember, we've got normal, otherwise known as valid, invalid data types, and boundary. Potentially we could also have erroneous, but it's not included here. So a normal data is 25, value's been accepted. We want an invalid, so this is going to be on the outside of it. So if we think about it, if we had, say, 310, that is greater than 300 and should give an invalid score. And then for boundary, it should be still valid, but right on the edge of what's accepted. So we could do 0 or say 300. And what should be expected is that in this case, it will be value accepted. Potentially, you could also say the boundary is right on the edge on the other side, i.e. -1 and 301, except of course this time the expected result would have to be invalid input. Okay, we're looking at the topic of Boolean logic and logic gates. Now with logic gates, there are 3 logic gates you need to learn about. There's the AND gate, the OR gate, and finally the NOT gate. But you have to learn how to draw them. And luckily, I'm a terrible drawer, so you can be reassured that you can do it yourself. With an AND gate, start with a straight vertical line, and then you're going for something that looks a bit like a D. How many inputs? Well, there are 2 inputs, and then there is 1 output. With an OR gate, what you do different is that you'd have a curved line at the start, and then you can go a little bit like an elongated D. Again, 2 inputs, A and B, and then an output. And then finally, with a NOT gate, we're talking about a triangle with a sort of bobble at the end, single input, single output. So that's how we draw them. Each of them have what's called a truth table. So with a truth table, we identify the inputs. So let me label this. So we've got A and B input, A and B input, and A input. My bad, the B is not even connected here. And then maybe we'll have something like, I don't know, O for the output. Do you know what? O is a terrible idea because it looks like a 0. S for output. There we go. And then we can do a truth table for all of them. So for the first one, we would do, so inputs of A, B, S as the output. And we do all the combinations. So what we've got is A and B are off. A is off and B is on. A is on and A is on and B is off. And finally, they're both on, which are all the combinations we can have here. We are going to need the same with an OR gate. With the NOT gate, you can see it's going to be different because actually we've only got a single input A, a single output S, and then we can draw our little more condensed truth table. But this time, all we have is A being 0 or A being 1. Great. Okay, with an AND gate, the one that's special is if both are on. If A and B are both on, then the output will be 1. Otherwise, it will be 0. Imagine the metaphor I use is a lock is a safe with 2 locks. Both locks have to be turned on for the safe to open, otherwise it won't open. With an OR, my example is, let's say you want to unlock your phone and you have a fingerprint reader and you also have a face unlock. If the face unlock will unlock it, the fingerprint will unlock it. Both of them together will unlock it, but if you use neither, it won't happen. So the special case with an OR is when both are 0, the output will be 0. Otherwise, it's going to be 1. And with a NOT gate, all it does is it flips it. So if it's 0, it becomes 1, and 1 becomes 0. Okay, great. Then let's use this to look at our problem. So it's A and B, so that's this one, and then that's going to be NOT. So A and B, so 0 and 1, so we can see here 0 and 1 should be 0, but because it's not 0 would make, in this case, 1. And then 1 and 0 again would be A, if A is 1 and B is 0, that would be 0, as you can see here again in our problem. Would that be 0? But because not 0 would make 1. Okay, this is a very typical Boolean logic question using logical circuits where you're given a logical statement and then you have to translate this into a logical circuit by combining logic gates. A cinema uses the following criteria to decide if a customer is allowed to see a film that has a 15 rating. Customers have to be 15 years age or older to see the film. So that's the first statement we want to make sure we include. So the customer has to be 15 years or older to see the film, but they also need to have either a ticket or have the money to buy a ticket. Okay. And then underneath here, there's a table to show the inputs the system will have. So A, the customer is 15 or over. B, the customer has a ticket. Or C, the customer needs the money to buy a ticket. So I'm going to put my inputs here first of all. So I'm going to do my 3 lines for my 3 different inputs. So I've got this one. In fact, I've got, let me just label them A, B, and C. And each of these are lines coming in. Okay. So the customer has to be 15 or older over, so that's a guarantee. While the other one is the customer has a ticket or has the money to buy a ticket, or as they've highlighted here. So I think we're doing OR. Let's draw ourselves an OR gate. And what's going to go into our OR gate is going to be B and is going to be C. And then this has to be true. They have to get the ticket, but they also have to be over 15. So if both have to be true for it to work, what kind of a logic gate is it? That's right. It will be an AND gate. So the OR gate will go in here. So either they've got the ticket or they have the money to buy a ticket and they have to be over 15. And then that's our output. Okay, this is a quite straightforward where we just have to identify these 2 logic gates to get us started. The logic diagram below shows a system made of 2 connected logic gates. Label these 2 gates. Okay, so do you remember with the flat and it looks like a bit like a D, that would be a AND. Whereas the triangle with the bobble at the end, that's an NOT gate. We now have to do a truth table, but this truth table, we're not going to just be using an AND, an OR, and a NOT. We have to apply it to the actual logical circuit. We've got our values of A and B and all the combinations. So if A and B are 0, so A and B in an AND gate would be 1. But then it goes through a NOT. So NOT 0 would be 1. In fact, remember what I said was the one special case with an AND gate is when both A and B are 1, the output would be 1. But not 1 would be 0. Remember, in all other situations with an AND gate, so it's 0 and 1 or 1 and 0, the outcome is going to be 0. But it's not 0, so all the other ones in this case would be 1. Okay, a little bit of a different one here. We've been given a logic diagram that we need to draw based on this logical system. And I'm really glad we're doing this question because it allows me to give you a few tips. So first tip I'm going to give you is look at all our different incomes of A, B, or C. Let's just put them out here, A, B, and C, because these are going to be our inputs. Okay, how do I do this? Work from the inner bracket first. So the first thing I'll do is this one, the B and C. So I'm going to draw this first. So remember, straight line, bit like a D, and then B and C are going to go into it. Then after that, I'll go the next one out. So it will be the OR. So this one will be the OR gate. But what's going to happen is that the A is going to, oops, that's really terrible, even for me. The A is going to go in here, the B is going to go in here, and then the outcome. What's the outcome, the label going to be? It's going to be P. Now let's have a go at this. It's asking us to complete this truth table. 0, 0, 0, 1, 1, 0. The last combination in here would be 1 and 1. Not A or B. So we need to evaluate A or B first. What's the one special circumstance with A or B is when both are 0, it will be 0, because not 0 is 1. 0 and 1 with an OR gate would be 1, but of course we flip it. So actually in this case it will be 0. What do you think the last two are going to be? Well, hopefully you deduce that 1 and 0 would be 1 again, but not 1 would be 0. 1 or 1 would be 1, but not 1 would be 0. We're now looking at the topic of programming languages and IDE, Integrated Development Environment. And we're looking at beginning the concept of languages. Recall that when you write code, you're writing code using relatively something that looks like English in your high-level programming language, such as Python. But in the end, at the machine level, the machine only understands ones and zeros. Your code didn't start like this. This is at the machine level. Your code started something like, and you can start with human readable source code. So this is a wonderful bit of code that doesn't do very much. But you can see that this doesn't look anything like this. However, for it to run on a computer, you need to take this human readable source code and turn it into machine code. And you do that by translating the human readable source code, in this case in a high-level language, into machine code. If it's a high-level language, you need to use either an interpreter, which will do it one line at a time into machine code, or you use a compiler, and a compiler takes all the code in one go and then turns it into machine code. And they have different advantages and disadvantages, which I'm sure we'll get into. The other type of language or family languages are what's called low-level languages. And these are low in the sense that they are closer to how the machine works. An example of that is something like this, which is an assembly language, where you could have a command like to load what's in memory location 4, to add that to what's in memory location 3. Those will be sent to the arithmetic logic unit, the value stored in the accumulator, then you store that in value 6 and output it. You see here one line can into one line of machine code, and this assembly language still not ready to run, even though it's a low-level language, because it needs to be translated into machine code. But this time you use what's called an assembler to turn it into machine code. Okay, well that was our overview. Now let's look at the question. Harry is planning to create a computer game using a high-level programming language, like for instance Python. State why the computer needs to translate the code before it's executed. Well, as we discussed earlier, it's not ready to run on the machine until it's in machine code. So it needs to be converted to machine code, as the processor will only understand machine code. Harry can use either a compiler or an interpreter to translate the code. This is what we were talking about earlier. Recall, a compiler looks at the code and in one go turns all of it into machine code, while an interpreter converts it into machine code line by line. And these have advantages and disadvantages. We need to describe two differences between how a compiler and interpreter would translate Harry's code. So a compiler would translate all the code in one go. And how did an interpreter work? That's right, an interpreter translates one line at a time. Okay, well that's one difference. Let's think about something else, about how errors occur. Well, when you compile, all errors are discovered as it goes along, but then ultimately you then get it reported at the end. With an interpreter, it stops when it finds an error. So it will interpret each line, and actually it will start running some of the code, and then will actually stop when it gets to the line where there's found an error. So a compiler reports all the errors at the end, whereas an interpreter, well, it stops when it gets to the point where it finds an error. If you recall, an interpreter is what's used on a web page for the JavaScript on it. And so actually it would run the code right until the point that there's an error, and then it would stop running. Also, it's worth knowing where the compiler works is it actually creates the ones and zeros ready to run, so the executable, or interpreter, it will always need the original source code to allow it to run in the future. Okay, some more questions on languages, and in particular the differences between high-level code and machine code. Graham is a freelance programmer. He has written a program for a client and gives the client both the high-level code and the machine code of the program. From our previous question, recall this is the high-level programming language and this is the machine code ready to run on the machine. So they're saying that they furnished with both this and with this. So describe what is meant by high-level code. Who is high-level code aimed at? High-level code is written and aimed at humans. So it's orientated for humans, as opposed to, of course, machine code, which is written so that the CPU, so the processor understands. What else? Well, it contains words close to English in a natural language. Is it ready to be run? No. It's going to need to be translated before it can be executed. Also, the code itself could then be actually compiled or interpreted to run on many different systems. It's what you talk about being machine independent, portable to different systems. Okay, well, what about machine code? A lot of what we said previously, you can just essentially flip, and that would make sense for it. So where we said that high-level code was human-orientated, well, machine code, we'd say that it's code meant to be executed on a CPU, and it's not meant to be read by humans. What does machine code actually look like? It looks like a bunch of ones and zeros, i.e. binary instructions with opcodes and operands. Where we said that high-level code is machine independent, we can say that in this case, it's machine dependent, because once it's been compiled or interpreted, it's only meant to run on that particular machine. Where we said with high-level code that it needs to be translated before being executed, well, in the case of machine code, it's ready to run, so it does not need to be translated. Finally, state why Graham needs a compiler. Or without the compiler, he won't be able to turn his high-level code into machine code. What else can the compiler do? Well, it also will help you pick up syntax errors. Remember, when you've run your Python code, often it won't run if you've made it won't ever run if you made a syntax error, and then it will spit back some errors and it will say the line it was on. It's the compiler that's doing that for you. Okay. In this question, it's going to ask us to compare high-level languages to low-level languages. In here, you're only allowed to include a single tick per row. Uses English-like keywords such as print and while. that's definitely going to be high-level language. So when we do or use Python, we're using things like print and while. If we're using either assembly code or machine code, which are low-level languages, we won't be. Must be translated before the processor can execute code. Now, I can't say I like this question because, of course, if the low-level language was assembly language, then you do need to translate that to run. But if the low-level language it's talking about is machine code, it is ready to run. A high-level language always needs to be translated. So in this case, we're going to say it's a high-level language. The code written is portable before different processors. Now remember, if you've actually have it turned into machine code, it's now dependent on that system. Whereas if you've written it in a high-level language, then you can recompile or reinterpret for a different platform. Finally, requires the program to understand the processor's registers and structures, so you really need to understand how the processor works. That's not necessarily in high-level language because the compiler or interpreter is doing that work for you, but it is for a low-level language. Describe the advantages of writing a program in high-level language instead of assembly languages. We looked at human-readable source code. So this was high-level languages, which is more like Python. And then we talked about assembly languages, where you've got mnemonics like LDA and for and add and 3. And which one do you think was going to be easier for us to be able to program in? What are the advantages? Well, what we can say is maybe it's easier and quicker for humans to write. It's also going to be easier to read and understand. And as a result of that, it's going to be much easier to maintain and debug. Now, you might be sitting there thinking, wait, it is not easy to write Python or to understand it or to debug it. But it's not saying is that easy, it's saying is that easier to write this, then it's going to be easier to write in assembly. Something that's very important though for you to hear right now is if you say it's easier to use, that is considered too vague on the mark scheme. So make sure that you say specifically it's easier for humans to write code than assembly language. It's easier to read and understand than assembly language. And it's easier to maintain and debug than assembly language, which would be acceptable. Now we're looking at the next stage, which we're looking at IDEs, which stands for Integrated Development Environment, where it wraps a bunch of the tools together so that instead of having to use a notepad and a separate compiler, it actually does the translation for you. It helps you identify errors. It provides functionality like breakpoints and to stepping to allow you to code more straightforwardly. So let's look at our problem. Jim is writing a program to calculate the wages of workers in a teddy bear factory. Jim uses an integrated development environment to create this program. Describe two tools in the IDE that help Jim when creating the program. One of the substantial things the IDE provides you is the ability to have an editor. This editor provides you some functionality like, for instance, color coding keywords. You know, like for instance, print or input, you'll note, or file, or while or for, you'll notice they've been color coded when you've been editing your code. What else does it do? Well, it can highlight syntax errors. Often there'll be sort of red squiggly lines that are able for you to see. Okay, what else apart from being an editor that does these things? Well, the other thing it can do is it can help debugging. So there's debugging tools. What sort of things are debugging tools? Well, you can have breakpoints that report the variables at a certain point. I think another major thing that we want to include, I know it's only 2 points, but of course in the background it helps you transform or translate your code in either a compiler or an interpreter. Great. Okay, let's move on. The area of a circle is calculated using this formula pi r squared, and we've seen this actually in an earlier question. In this one here, it's just giving you the scenario, which was actually another question, but it's saying here, what are two features of an IDE that might be used when writing the program? You know what I might do? I might just put a list of all the acceptable things you could include, and then you can be furnished with a full list of what sort of facilities a IDE makes available for you. So there's error diagnostics, where it might highlight some syntax errors. It might provide a runtime environment with a translator able to actually compile or interpret it into machine code. You may have an editor with things such as maybe auto-indenting or making suggestions for your code, and of course highlighting keywords. You may set a breakpoint for the program to run to and then report what the variables are at this point. Very good for looking for things such as logic errors. And then there is stepping, where you run your code a line at a time, a bit like an interpreter would do, I suppose, and then you can help identify where the code went wrong. Again, it's great for things like logic errors. Okay, in these final questions here, I've labeled them combined questions. Why are they combined? Well, if you look, they're using all the skills that we identified earlier. If you look, you see here, it's talking about defining a high-level language, about debugging this code, about finding an error line, correct the line of code, about the tools in an IDE, how you could use a compiler or an interpreter, and how they would use different in an IDE. We've covered this earlier, so you know what I'm going to do? I'm not going to put the answer here right now. I'd like you to attempt this answer, and then at a later point we'll cover and see how you've actually done. In this question here, it's very similar, except it's saying finding two tools or facilities an IDE commonly provides. And again, we've covered this previously, so I'm not going to do it right now. I'd like you to have a go at doing this yourself.